Good morning, everybody. We present a method for time delay estimation in unresolved lensed quasars via convolutional neural networks. A common method to estimate the Hubble constant is the measurement of the time delay between multiple images of a lensed quasars via light curves. For example, this beautiful image of RxJ 1131. This image is taken from the Hubble Space Telescope. This can be done by surveys using large telescopes. These telescopes can indeed resolve the lensed images. The problem is that the time in this telescope is precious, and normally it is not possible to achieve long-term monitoring. On the other hand, small telescopes cannot resolve the lensed images normally, but they are less congested, so they can achieve in principle long-term monitoring. So it could be great to achieve time delay estimation if we could do it on unresolved lensed quasars light curves. In fact, if you look at the distribution of known gravitationally lensed quasars as a function of the number of multiple images, you could see that this gray region contains the 70% of the total gravitational lensed quasar sample. The maximum separation in this area is 2 arcseconds. And we know by experience that this is a typical thing of small-sized telescopes that are not placed in top astronomical sites and that have no high angular resolution technologies such as adaptive optics. So we decided to simulate unresolved curves pairing couples of lensed images from an artificial system that we call System A and RxJ 1131. We use a convolutional neural networks that we call CNN to retrieve time delay from light curves of unresolved quasars. We use artificial data to train the convolutional neural network model. Inference is then performed on the original non-resolved light curves using the trained model. In these figures, on top, you can see the intrinsic variability of System A and the intrinsic variability of RxJ 1131. Using a simulation software, we then simulate 4 light curves from 4 components of System A and for the 4 components of RxJ 1131. Then, we pair these 4 images 2 by 2 to produce an unresolved light curve. We then have 10 unresolved pairs for each one of the systems. We repeat the simulation several times, and then we use the convolutional neural networks to calculate the time delay. We compare our results with other kinds of neural networks, and our simulations show that our convolutional neural network model performs better with respect to other neural networks. We are ready to apply this method to real data. In particular, these 2 plots show the kernel density estimation for our CNN model in blue and for other 2 neural networks in red and in green for the System A and for the other quasar RxJ 1131. If you are interested in our method, more details are given in our archive paper that we recently submitted. Thank you very much for your attention and enjoy the rest of the conference.